The problem statement from GATE Physics 2018 reads as follows. In a 2 to 1 multiplexer as shown below, the output X equal to A naught if C equal to 0 and the output X equal to A1 if C equal to 1. And we have been given this 2 cross 1 multiplexer in this diagram here with two inputs A0 and A1 and one control line C, and the output is X. Now the question asks which one of the following is the correct implementation of this multiplexer, and we have been given the 4 options and we have to choose the one correct option. This is only one option is correct for this question. Let's first talk a bit about the multiplexer, what a multiplexer is. So the key feature of a multiplexer is that it has 2 to the power, it can have 2 to the power n input signals, right? And to control those 2 to the power n input signals, it has n select signals, or they are sometimes also called the control signals or control lines. However, only one input is routed to output. So only one input is connected to the output. Now how do we know which input to select? That is chosen based on the select or control signal. So what I mean to say is that, let's say this is a 2 cross 1 mux. Okay, why we are calling it 2 cross 1? Because there are two inputs, A0 and A1. So essentially for this question we have n equal to 1. So because we have one select signal, note that this signal is been denoted by the alphabet C here. So if n equal to 1, this is the control signal, number of control signal, which is 1 here, and inputs will be 2 to the power n, so which will be 2 to the power 1 equal to 2. These are the input signals. So we'll have two input signals. So you can see those two input signals, A0 and A1, and only on a given condition only one of these inputs, either A0 will be connected to X or A1 will be connected to X. Okay, so what you can assume is that as if there are two switches here, you can see one switch in red and the other switch in blue. So you can assume that only one at any given point of time, depending on the value of C, is either red switch will be connected or blue switch will be connected. Now in order to express this is given in the question that output X equal to A0 if C equal to 0. So we have written when control select signal is 0, what is the value of output? Output is A0. This is given. However, if the control or select signal is 1, then the output is A1. So this is the truth table for this 2:1 multiplexer, and this is the logic that we were given and we have implemented. This is the schematic and this is the truth table for this 2:1 multiplexer. Now I have just replicated the same statement, this same statement that output X equal to A0 if C equal to 0 and X equal to A1 if C equal to 1. I am just replicated this here. Now let's first look at only the first row. So it says that when control signal is 0, the output is A0. So what we can assume is that as if this switch is closed. I told you can assume that as if there are two switches, right? So if C equal to 0, we will assume that the top switch is closed, so X, whatever the value of A0 is, will be fed to X. In terms of Boolean algebra, I can write is that X0, let's assume this value to be X0 for the time being. Okay, so X0 will be what? It will be A0 times C bar, because C equal to 0, C bar would be 1. So it will be X0 will be A0 times C bar, right? And I can write this as, this is an AND gate. Note that this is a dot in between, right? This is the multiplication. So I can simply write that X equal to A0 dot C bar, right? And similarly I can implement this logic using an AND gate. So first input, this is X0, so first input is A0 as you can see here, and the second input is nothing but C bar. So this is C, and this circle that you see here denotes that the input to this AND gate is C bar, right? So I've implemented the first row here. Now let's go ahead and implement the second row. So in the second row in blue says the control signal is 1, you can see that X equal to A1. So this is the row I am implementing. Again I can assume that as if when C equal to 1, the bottom switch is closed, which I am denoting by this down arrow, right? So then I can write the output as, let's denote this by X1 equal to A1, it's directly passed on here, times C. Why times C? Because it's true only when C equal to 1. So again I can do it, this dot denotes this is an AND gate, so I can again implement X1 as an AND gate of one signal is A1, the second is C. So I have written both of them like this, in this fashion here. Now note that these are truth table. So either first row will be true or second row will be true. Both cannot be true simultaneously. So what I can write, that final output x will be nothing but x naught or x1. Please note that this term came because either first row will be true or second row will be true. So I can write the output x, final output x will be x naught or x1. So I can write it as x naught plus x1, and I know the value of x naught, right? So this top half that you see is nothing but x naught. Note that this was the x naught, a naught and c bar. So you see this top thing is nothing but x naught. So I might as well write here x naught, right? Similarly, this thing that you see at the bottom is nothing but x1. So I'll write this as x1. And what is the output x? I know that the output x is x0 or x1. So I put this OR gate, and first input is x0, second input is x1, and I'll simply get the output x here. So output x will be x0 plus x1, where x0 is a0 times c bar and x1 is a1 times c. Right. So what we got was that this was the logic gate diagram that we obtained for this 2x1 multiplexer, right? In the last slide we saw that. Now we can clearly see that which one of the options does it match. So it matches that. So first is a0 c bar, so this is a0 into c bar, and the second is c into a1. So yeah, option A matches exactly. Now note that we'll check the other option. So this is a0 times c, which is not correct. It should be a0 times c bar. Again, this is an OR gate, so this cannot be correct. This has to be an AND gate. These are AND gates, but there's no a0 times c bar here. So only option A is correct. And yeah, so that's it. We have solved this problem for the multiplexer. It was a fairly straightforward problem if we know how a multiplexer operates, which we saw in the theory part. So and then we finally implemented using very simple 2-input logic gates. Right, so option A is the correct. Thank you for listening.